We've established how deterministic decoding ensures that every generated text remains consistent. Now let's take it one step further. How do we actually identify the true causal effects hidden in our data? This is where nonparametric identification comes in, allowing us to estimate the impact of different treatments without making restrictive assumptions about the underlying data structure. In other words, we let the data speak for itself. At the heart of this approach is the concept of the average treatment effect, often referred to as AT. This measures the difference in expected outcomes between individuals who receive the treatment and those who don't. Think of it as comparing two possible realities, one where someone gets the treatment and one where they don't. The ATE is simply the average difference between these two worlds. Now, here's where it gets tricky. Simply comparing treated and untreated groups isn't enough. Why? Because in the real world, people aren't randomly assigned to treatments. There could be underlying factors like education, experience, or personal preferences that influence both the treatment and the outcome. If we don't account for these confounding factors, we might mistake correlation for causation. To solve this, we introduce a deconfounder. Think of this as a filter that helps us isolate the true effect of the treatment. Instead of just looking at raw treatment effects, we first adjust for hidden biases by summarizing all the possible confounding influences into a single, more manageable representation. This ensures that we are comparing apples to apples, not apples to oranges. Here's how it works. Once we adjust for the deconfounder, the treatment assignment should become completely independent of the outcome. This means that any difference we observe between the treated and untreated groups can now be attributed to the treatment itself, not some hidden bias. What makes this method so powerful is that it doesn't rely on rigid mathematical formulas or predefined assumptions about how variables interact. Traditional methods often assume that relationships between variables follow a simple structure, like a straight line equation, but in reality, relationships are far more complex. Non-parametric methods don't force the data into a fixed mold. They adapt to the complexity of real-world interactions. Of course, there are challenges. If our deconfounder isn't properly estimated, we might still have some unobserved bias lurking in our data. That's why ensuring enough variation in the data and using the right machine learning techniques to extract meaningful representations is critical for accurate causal inference. But here's where things get even more exciting. Now that we know how to identify causal effects, the next step is putting this into action. Next, we'll dive into estimation and inference, where we'll actually measure these effects with precision. Stick with me because this is where causal AI starts making a real-world impact.